Today we're going to talk about mid-segments in the triangle. Suppose I have a triangle and I take the midpoint of one of its sides, for example here. Then I'm going to draw parallel lines through that point to the other two sides. So this line is parallel to this line and this line is parallel to this line. The first thing that we're going to notice here is that this quadrilateral here is a parallelogram because it has two pairs of opposite sides that are parallel. This side is parallel to this side and this side is parallel to this side. So we can mark the red angles as shown. This angle equals this angle equals this angle equals this angle. Another thing we can notice is that this green angle here equals this angle here because, again, of the parallel lines. And because of the other two parallel lines, we have that this angle here, the blue angle, equals this angle. Firstly, from the properties of the parallelogram, we have that the two pairs of sides that are parallel are also equal in length. And so I can mark the sides of the parallelogram like this. The next thing to see is that this triangle here and this triangle here are congruent because they have the same length of the side here and here, and they have the same angles. This angle equals this angle, this angle equals this angle, and this angle equals this angle. And because they're congruent, they have equal sides. All their sides are equal. So this side equals the corresponding side in the other triangle, which is this one, and this side equals this one. Finally, let's take this diagonal of the parallelogram. Then we have that this triangle is congruent to this triangle, because they have two pairs of sides that are equal. This side equals this side and this side equals this side, and the angle between those sides is also equal, so this angle equals this angle, and so they're congruent, and therefore they have equal angles, and this side equals this side. We have, for example, from the large triangle that the sum of the red angle plus the green angle plus the blue angle is 180 degrees, and so we can find this angle here because the straight angle here is 180 degrees, and we have one red and one green angle, so the third one must be blue. And similarly here, the third angle here must be green. And this is the full picture. So see what we've got. We've got a triangle, and these 3 points are the 3 midpoints of each of the sides. And we connected 2 of the midpoints here, the other 2 midpoints here, and the other 2 midpoints here. And we got a small triangle. And it turned out that the 4 triangles on the picture, the 4 small triangles, this one, this one, this one, and this one, are actually congruent to one another. They all have equal sides and they all have equal angles. And so it turned out that this side is parallel to this side is parallel to this side, and this side is parallel to this side. And also that the length of this segment is half the length of the base of the triangle. This segment here we call the mid-segment of the triangle. So anytime we have a triangle, for example this triangle, and we took 2 midpoints like this, we call this red segment here the mid-segment of the triangle. We know that one of its properties is that the length of this mid-segment is half of the length of this base of the triangle, and also that this mid-segment is parallel to the side of the triangle. Now let's recap by listing the possible ways in which we can get mid-segment. So the first one was we have a triangle, and then we choose a midpoint, and we choose another midpoint, and we just connect them, and then we have a mid-segment. So we have parallel lines, and we have this length is half of this length. The second way is to take a triangle and take one of its midpoints, the midpoints of one of its sides, and draw a parallel line, a line that is parallel to the base. So, for example, these two angles are equal. And so this is the mid-segment of the triangle with respect to this side, of course. And so we can mark that this is a midpoint, and also that the length of this is half of the length of the base of the triangle. The third way would be take a triangle and take a segment like this, such that this line is parallel to this line, and its length is a half of the length of this side. Then this is the mid-segment in the triangle, because we know that any other parallel segment that's different than this one would have a different length than this one. So this here would be larger, and this here would be smaller than this. And so the one that has length exactly half of the base is unique. And we already know that for the mid-segment, it is a segment for which this length is half of this length. And so they coincide. This is the same mid-segment. And these are the only 3 ways in which we can 100% define a mid-segment. And now I'm going to show you an example where we could think it's a mid-segment, but it's actually not. Suppose I take this triangle, in which I took a midpoint, and then I constructed a segment inside a triangle, such that one of its endpoints is the midpoint, the other endpoint lies on this side, and its length, let's say if it's x, then the length of this side is 2x, so the length of this is half the length of this base of the triangle. And then you could think that this is actually a midsegment because it satisfies two of the properties of here, for example. But it might actually not be the case. As you can see, this line is definitely not parallel to this line. And here's why it's not a midsegment. Well, let's draw the actual midsegment in the triangle. Then of course it would have a length of x, because its length is half the length of this side. And it would be parallel to this side, and so this angle would equal this angle. And then we can have a isosceles triangle here, such that this angle equals this angle. And this is how we could construct this segment here. That's a fake midsegment. It's not actually a midsegment, although it might look like one. Lastly, I want you to imagine the midsegment as a homotety with center this point and coefficient 1/2. Something that should look like this. So we essentially rescaled this triangle such that this point here stayed in the same place, and we moved this line here. Now, because the coefficient is 1/2, all distances got scaled by 1/2, and so this distance is half of this distance. This one is half of this one, the whole thing, and then this one is half of this one. Also, this side is parallel to this side, because if we apply homotety to a line, it goes to a line that is parallel to the original, and the angles are preserved. So for example, this angle equals this angle, and this angle equals this angle. This triangle is similar to this triangle with coefficient 1/2, because the sides of this one are half the sides of the large one. So the picture looks like this. And you can also think of these properties as a special case of the intercept theorem, because according to the intercept theorem, the ratio of this divided by this equals this divided by this, and it equals this divided by this, which in this case is just a half. It turns out that we can define a midsegment not just for a triangle, but also for a trapezoid. Consider this trapezoid where this side is parallel to this side, and then take the midpoints of this side here and this side here. And then this line turns out to be a midsegment in the trapezoid. What does that mean? Well, it means that this line is parallel to this line and this line, and it also means that if this length is x, and this is a, and this is b, then the length of x equals the sum of a and b over 2. To prove this, I'm going to choose a point here on this side, such that this line is parallel to this line. Then we know that this quadrilateral is actually a parallelogram, because this is parallel to this and this is parallel to this. Because of the parallelogram, we know that this side equals this side, so this is b, and hence this is a minus b, and we know that this length equals this length. Now if I take this point to be the midpoint of this side, it will follow that this length equals this length. But we know that this line is parallel to this line, and therefore this quadrilateral is actually a parallelogram. It means that this line is parallel to this line. But on the other hand, this line here, defined by these 2 points, is parallel to this line here, because this is a midsegment in this triangle because of the midpoint here and the midpoint here. And therefore, this line is parallel to this, which is parallel to this, which means that this point, and this point lie on the same line. That line is the midsegment of the trapezoid. And now look at this triangle with this midsegment. We know that this is a minus b, and therefore this length is half of that, a minus b over 2. And we know that this is a parallelogram, and therefore if this is b, then this is b. And so the length of the entire midsegment is b plus a minus b over 2, which is exactly equal to a plus b over 2, as we wanted to show. In conclusion, if we have a trapezoid, and we take the midpoints of the two pairs of opposite sides that are not parallel, then the segment between these two midpoints is called the midsegment of the trapezoid. It is parallel to the two parallel sides of the trapezoid and has length a plus b over 2, where a is the length of this parallel segment and b is the length of this parallel segment. And this is the optional problem. Suppose we have a parallelogram here, and we took the midpoint of one of its sides, and then we connected the midpoint with this vertex here, and we dropped a perpendicular from this point to this new line. And now we need to prove that the length of this side of the parallelogram equals the length of this segment here. So the two blue segments have equal length. And here's the solution. Notice that the length of this segment is half the length of the whole segment, which equals the length of this segment because this is a parallelogram. And in a parallelogram, the pairs of opposite sides have equal lengths. And also, this segment is parallel to this segment. We have a segment that's half the length of this one and parallel to it. And this reminds us of a midsegment. Suppose that I continue this side like this, then in this triangle, this would be a midsegment. See, this segment is parallel to this segment, and its length is half of this length. And so in this triangle, this must be the midsegment. And therefore this point is the midpoint of this side, or this equals this. Finally, take a look at this triangle here. It has a right angle, and so it's a right angled triangle. And this here is the median to the hypotenuse. But we know that the median to the hypotenuse in a right angled triangle always equals half of the hypotenuse. And so this length equals this length equals this length. And we're done.